Ladies and gentlemen, welcome back to lesson 12 in this course in group theory. This course is all about groups, but now we're talking about subgroups as well. In lesson 9, we introduced what a subgroup is. We've given you some examples on subgroups, and we've seen what their properties are. We've seen subgroups in symmetric groups, subgroups in dihedral groups, and subgroups in cyclic groups. So we've seen all kinds of subgroups. But is there a way to generate these subgroups? Is there a way to take, let's say, a subset of some elements in the group and create a subgroup using these elements? Well, absolutely. That's what today's lesson is all about. It's about creating subgroups. And not only that, I'm going to show you how Sn and An are generated. So we take specific permutations, and I'll tell you that we can generate the entire group Sn or the entire group An using only these elements. And we can take as well some elements in the special linear group and generate the entire special linear group just by using these elements. And lastly, we're going to be looking at the lattice of subgroups, a visual representation of how to show all the subgroups that they are of a group. And here is a quick example. We've taken cyclic subgroups before, Z6Z, the cyclic group containing 6 elements and its subgroups with orders 3, orders 2, and order 1, respectively. So just to refresh in your memory, this is the cyclic subgroup generated by 2, containing 3 elements, 0, 2, and 4. This is the cyclic subgroup generated by 3, containing 3 and 6, or 3 and 0, and this is just containing 0, the trivial subgroup of the cyclic group Z6Z. So the cool thing about this is that once you know that your entire group or your entire subgroup is generated by certain elements, and you want to prove any property regarding this group or this subgroup, then it suffices just to use those elements, just to see if the property works for those particular elements. Because you know that if it works for those elements, and those elements generate the entire group or the entire subgroup, then definitely it works for the entire group, and you have done your proof. So it's a very cool way of reducing a lot of effort, a lot of work in trying to prove something, trying to prove a property for these groups. So with that in mind, let's get started. Let us start with the definition of the subgroups generated by subsets. Let G be a group and S a subset of G, so any collection of elements in G. So we have the subgroup generated by S is the smallest subgroup containing S. Simple as that. The smallest subgroup that contains the elements of S. In other words, it is the intersection of H for all H subgroups that contain S. So basically, if you have S here, and this is your big group G, and you have a subgroup here, H1, containing S, you have another subgroup, H2, containing S, and let's say H1 and H2 are the only subgroups that contain S, you want to take the intersection. So the intersection, we've already proven before that the intersection of two subgroups is also a subgroup. So we can say that the intersection H1 and H2 is the subgroup generated by S. Simple as that, just take the intersection. So that is the definition of this structure here. We denote it by this notation that you might be familiar with before. If you're not, welcome. This is the first time to see a notation like that, where S is the subset in question. The elements of S are called the generators of the subgroup generated by S. The generators, meaning that you can produce any element in the subgroup generated by S using the elements of S. Now that we have defined the subgroup generated by S, we have defined it to be the intersection of all the subgroups that contain S. We want to answer these three simple but important questions. First of all, why is it a subgroup? We've already partially answered that, but I'd like to give a more formal, complete answer. Secondly, we have that the subgroup generated by S contains S. Why is that? It seems trivial, but I also like to provide a good answer. And lastly, why is the subgroup generated by S the smallest unique element in this set here that I'll be explaining now? But why is this the smallest subgroup containing S? So let's get into it. First, let us construct squiggly S. This is squiggly S. Squiggly S is the set of all the subgroups of G, H, such that S is contained in H. So basically, all the subgroups containing S. Squiggly S, note that it is not empty, because G is a member of squiggly S. G is in fact a subgroup of G, as we've seen in lesson 9, and S is of course contained in G. S is a subset of G. So because there is an element in squiggly S, it is non-empty. If it's non-empty, then we can take all the elements in squiggly S, we can take their intersection, and that will be our subgroup generated by S. And we can use the subgroup intersection proposition in lesson 9 to say that this is in fact a subgroup, not a subset. So we conclude that it is in fact a subgroup of G. The second question is, what is a subgroup generated by S contain S? All what we know here is that this is the intersection of all of the subgroups that contain S. But that is the case because of the definition. Because S is contained in H for all H in squiggly S, therefore S must be contained in their intersection. Here, if we have S being contained in H1 and S being contained in H2, then S has to be here, right? Therefore, the intersection of H1 and H2 has to contain S as well. So this is the subgroup generated by S, which contains S as well. So it's very simple here. And lastly, why is the subgroup generated by S the smallest unique element in squiggly S? Well, we want to show first that it is an element of squiggly S. But it is an element because, remember, what does qualify as an element? It has to be a subgroup of G and it has to contain S. But both of these are already met. It is a subgroup by the first part. It contains S by the second part. So we have that it is a member of squiggly S. Now, why it's the smallest unique element? Well, that it is the smallest precisely because, again, it is the intersection of all of the H in squiggly S. So for all H in squiggly S, H would of course contain the intersection of all the elements in squiggly S, which is precisely the subgroup generated by S. So to make this more clear, we have that if I draw H1 and H2, this would be the subgroup generated by S, which is the intersection of H1 and H2. But then H1, of course, will contain the intersection, and H2 will also contain the intersection. So any H in squiggly S will contain the intersection, therefore making it the smallest element in squiggly S. Okay, now that we got the definition and some important questions out of the way, I want to discuss a little bit the notation that we're going to be using. If S was a finite set, let's say S was composed of S1, S2, all the way to Sn, then we will write the subgroup generated by S to be equal to brackets S1, S2 all the way to Sn, instead of saying brackets, this set containing S1, S2 all the way to Sn. So all what we do here is write down the elements of S instead of writing S itself. Secondly, we have that if we have two subsets S and K in G, then instead of writing the subgroup generated by S union K, we can say the subgroup generated by S comma K. And that's it. So this here, using the definition that we've seen, would mean that it is the intersection of all the subgroups that contain the union of S and K. So sometimes in mathematics, we define an object. The definition is clear, simple, and consistent. However, it's not useful. It's not useful for our applications for now. So what do we do? How do we get around that problem? Well, we need to find a proper construction of what we're defining, another alternative definition, and we need to somehow prove that that definition is equivalent to our original definition. And therefore, that definition will not only be consistent with our original definition, but also very useful in applications. So, the thing we're going to do here is that we're going to define S bar to be something, and then we're going to prove that that definition equals the definition that we've seen of the subgroup generated by S. Remember, the original definition of that is that it's the intersection of all the subgroups that contain S. So it's not equal necessarily to this, not until we prove it. So what is that? What is S bar? Well, if you look at it, you see that we're taking elements Si and S. We're taking epsilon I to be plus or minus 1. And then we're taking the products of S1, S2, all the way to Sn, with the powers epsilon 1, epsilon 2, all the way to epsilon n. And if n is equal to 0, then S bar will just be containing the identity element. N is equal to 0, meaning that the set S is empty. So in words, we can say that S bar is the set of all finite products of elements in S and their inverses in S. So the elements in S are S1 to the power 1, S2 to the power 1, Sn to the power 1, and the inverses are S1 to the power minus 1, S2 to the power minus 1, and that's why we have the 1 and minus 1 there, is to see if the element is in S, or like we're taking the elements or the inverses in S. Okay, so this is all the finite products possible from the elements in S or their inverses. And the finite products are called words intuitively because the S's could be thought as letters. So when we group letters together, we get words. Now I'd like to note two things of importance. The first is that the SIs do not need to be distinct. We can have as many SIs that are identical as we want. For example, a square could be equal to a. So basically, if we have our S1 to be A, and our S2 to be A, and our epsilon 1, epsilon 2 to be 1 each, then we can group these A's together, we get A squared. So I never said that the S1, S2, Sn have to all be distinct, which even increases our possibilities for the finite products. And the second remark is that S bar is not necessarily a finite or even a countable set. Even though S could be a finite set, S bar is not necessarily one. Okay, now that S bar is well defined, we want to link it back to our original definition of the subgroup generated by S. This is exactly what the proposition claims. Let G be a group, S a subgroup of G, then we have that S bar is equal to the subgroup generated by S. Let's get down to the proof. Okay, to prove this proposition, we'd like to say that S bar is also a subgroup of G the same way that this is a subgroup of G. The first thing to do is to prove that S bar is non-empty. The reason S bar is non-empty is because 1 is contained inside S bar always for all n in Z bigger than or equal to 0. Because even if n is equal to 0, well, even if S is empty, we have defined S bar to be equal to the set containing the identity element. So the worst case scenario is that it contains one element. So S bar is always non-empty. The second part in proving that it's a subgroup of G is if we let S and R be two elements in S bar. If there are two elements in S bar, they could be written as a finite product, S1, epsilon 1, all the way to Sn, epsilon n, and the same goes for R, R1, epsilon 1, all the way to Rm, epsilon m. And we want to prove that S times R inverse is also an element in S bar. So it's also a finite product in the form that we've seen earlier in S bar. So let's see what SR inverse looks like. Calculating SR minus 1, we obtain S1 epsilon 1 all the way to Sn epsilon n times R1 epsilon 1 all the way to Rm epsilon m inverse. And now we simplify by saying this is equal to S1 epsilon 1 Sn epsilon n. And when we take the inverse of a product of elements, what we do is we reverse the order of all of the elements and we put every power to times minus 1. So it will start with Rm, and it's going to be minus epsilon m, and then followed by Rm minus 1 minus epsilon m minus 1, all the way to R2 minus epsilon 2, R1 minus epsilon 1. So just take the reverse order. Just like when we do AB inverse is equal to B inverse A inverse, we do it here, but for more elements. If you want to prove that more formally, you can use induction. So we have now a product of S's and R's and the epsilons up top. This, in fact, is an element of S bar. Because if you take epsilon I, this is either plus or minus 1. So if you take the negative of that, this is also plus or minus 1. So it satisfies the condition that the exponents are either plus 1 or minus 1. So this whole thing is a finite product which lies in S bar. This means that we have satisfied both conditions of S bar being a subgroup of G. So this means that S bar is in fact a subgroup of G. Now that we have proved it's a subgroup, we'd like to prove that it's equal to the subgroup generated by S. So now we prove that this is equal to that using double inclusion. Standard technique to prove that two sets are equal, we use double inclusions. So this means prove that, first of all, this is contained in that, and second of all, this is contained in that, the opposite direction. So this I will denote by star, and this I'll reference by double star. So to prove the first part, notice that we have that for all S in S, we can write S to be equal to S to the power 1, and this is nothing but a finite product with epsilon being equal to 1. So this is a member of an element of S bar. So all S in S could be written as an element in S bar, and because S bar is a subgroup, all the products of S, all the inverses of S, so we can write that since S is contained in S bar, as we've just seen right now. We have that the subgroup generated by S is contained in S bar. The second part can be proven by noticing that the subgroup generated by S is a group containing S. So because it's a group, it is closed. So it is closed under the group operation and under taking inverses. So because it's closed under the group operation, we can take any product we want and it'll be still inside the subgroup generated by S. And because it's closed under taking inverses, we can take the epsilons to be -1 and that will be no problem. It'll still be inside the group generated by S. So we can conclude it must contain all elements of the form that we have discussed earlier in the definition of S bar, S1 epsilon 1, S2 epsilon 2, all the way to Sn epsilon n, which all lie in S bar, of course. So since every element in S bar is contained inside the subgroup generated by S, by virtue of it being a group, then this means that S bar is contained inside the subgroup generated by S, therefore proving the double inclusion, therefore proving the equality. So this means that S bar is equal to the subgroup generated by S. So not only are they equal, but also it is the subgroup of G, so we can use these two sets equivalently. So S bar is exactly the subgroup generated by S. And this definition here is much more useful in our applications, at least, than the original definition that we've used. So if you think about it as the products of all the elements in S or the inverses in S, then it will be much easier to deal with. So that was the point of this whole proposition, and that completes the proof. Okay, now that we have found a proper construction for our subgroup generated by our subset S, it is time to look at some examples to see exactly how we can use this nice construction. So the first three that come to mind is the four-client group V4, the subgroup generated by the rotations in D to N, and the subgroups in the integers with the operation addition. So V4, if you remember, V4 is a subgroup of S4, the symmetric group. It is the subgroup containing the double transpositions. The double transpositions meaning the permutations that contain two cycles, such as 1, 2, and 3, 4. It contains 4 elements. It contains the identity, and it contains 3 double transpositions like that. We can see here that V4 can be generated by only 2 elements. So we can find the generators to be the double transposition 1, 2, 3, 4, and the other double transposition 1, 3, 2, 4. And we see that these 2 elements generate the entire group V4. Why is that? Because the identity element can be generated by one of these elements. It can be generated by taking this element, multiplying it by itself. So 1, 2, 3, 4. We know that the order of this is equal to 2. So if we multiply it by itself, we know that this and this will cancel out to give the identity permutation, and this and that will also cancel out, giving us the identity. Okay, now the last thing is to find how we're going to get the last double transposition, which is 1, 4, 2, 3. Well, simply put, if we multiply this element by that element, we get exactly 1, 4, 2, 3. And therefore, we have obtained all of the elements possible in V4. So we can say that these two elements generate V4. And we can simply write it as a generator, just like we've done earlier. If you remember in lesson 4, generators and relations, we have found that these two elements generate the entire group V4. The next example that comes to mind, in the dihedral group D to N, if we take the cyclic subgroup 1, r squared, all the way to r to the n minus 1, that could be just generated by a single element, which is r. Because any element of here can be generated by r if we take a power of r. So this is just r to the 1, and then r to the 2, r to the 3, r to the n minus 1, and for the identity, we do r to the n. And therefore, we can work only with r, and that will suffice to work with all of these elements. How cool is that? It will reduce a lot of calculation, a lot of effort. Just by working with a single rotation, we can work essentially with the entire subgroup. The last example talks about the subgroups of the additive group, the integers. To understand the subgroups of this group, we need to consider what the integers is. The integers, as we've seen in lesson 10, cyclic groups, is a cyclic group. So we can say that Z is generated by a single element, which is 1. Because any integer can be written as the sum of 1 by itself multiple times, or minus 1 by itself multiple times. It's generated by a single element, therefore it is cyclic. And we've seen that the subgroups of a cyclic group are also cyclic. So if we generate instead of 1, let's say we generate by the element 2. So we get 2, 2 plus 2, 2 plus 2 plus 2, and also minus 2, and minus 2 plus minus 2, and minus 2 plus minus 2 plus minus 2. We get exactly the multiples of 2. We get the even numbers. So the even numbers are 0, 2, 4, 6, minus 2, minus 4, minus 6. And this is a subgroup of Z. It is a subgroup that is generated by a single element, which is 2. So it also is a cyclic group. It's a cyclic subgroup of Z. And if we take another integer, say 3, we would get the following subgroup. We would get 0, 3, 6, minus 3, and minus 6. In other words, all the multiples of 3. That would be another subgroup of the integers. And you can see that every element here is an additive power of 3 because it is obtained by adding 3 to itself multiple times or minus 3 to itself. And minus 3 is the additive inverse of 3. So it is very consistent with the definition of the subgroup generated by 3 that we've seen, the S bar. The S bar, which is basically that. And here, the only element, the only generator in S is 3. So we can just add 3 to itself or add the inverse of 3 to itself. We can also, of course, add 3 to the inverse of 3 somehow along the line, but we know that this will just cancel out, so we don't bother adding that possibility in our head. But it is there. It is important to see that this is a finite product, so it is an element in the subgroup. So instead of 2 or 3, we can use any integer we want. So essentially saying that the subgroups of Z are all of the form m times Z, and this equals the set of m times k, where k varies through all of the integers. So this is generated by a single m, a single integer m. So it could be m is equal to 2, m is 3, m is 5, 7, m is 11, 16, 32, any integer we want, and it will give us a subgroup of the integers. Moreover, not only these form the subgroups, these form the only subgroups of the integers. There are no other subgroups. So all of the subgroups of z plus are of the form mz, the exact form that we've just seen now. The next topic of discussion is one of my favorites. It's very interesting how these specific groups are generated this way. So generating an and sn goes as follows. The first thing to note is that we've said that any permutation in sn, by the way, if you've forgotten what sn and an are, I highly recommend you go back to lesson 5 in symmetric groups and check it out. So Sn is generated by just two cycles. Two cycles are cycles which contain two elements. And we've said that that's because any permutation can be written as a product of transpositions. And a product of transpositions is exactly what it means to generate the entire group of permutations. That's why this has already been proven. Now, an is sort of the same as Sn, except that an deals with only even permutations. Even permutations contain an even number of transpositions. So that's why they are generated by not two cycles, but two cycle pairs. So you have to take a pair of two cycles to make an even number of transpositions. A transposition, remember, is just a two cycle. Okay, the thing that is interesting here is that an can be generated by three cycles. So we can discard this less useful definition of an and take the more useful generation by three cycles for n bigger than or equal to 3. To prove this equality of sets, we will prove it again by double inclusion. We will prove first that the three cycles is contained inside an, and then we will prove that an is contained inside the three cycles. So to prove that the three cycles are contained in an, we want to say that any three cycle is an even permutation. And why is that true? The three cycles are even permutations since A, B, C, any three cycle can be written as AB, BC. So the way I did it is I just looked at where A is being sent to. It's sent to B, so I'm writing it as AB. And I'm looking at where is B sent to. It's sent to C, so I wrote B sent to C. And I close it up and I see that, oh, well, C is sent to B and B is sent to A, so essentially C is sent to A just the way I want it. So I can write any three cycle as a product of two transpositions, so an even number of transpositions, so we call them even permutations. So if we take the subgroup generated by three cycles, since all the three cycles are even, then this contains the even, and it's going to be contained in an, since an just contains all of the even permutations. And that is the first inclusion. For the reverse direction, we will first consider the case, the trivial case, where n is equal to 3. So if we have three elements in our set, we consider the permutations on these three elements. What do we get? So for n equals 3, we will just be listing A3. So A3 contains the elements, the identity. Let me just write ID for identity, and 1, 2, 3, and the inverse, 3, 2, 1. And these are all the even transpositions. There are no others. And this definitely contains all of the 3 cycles, so I can just say the subgroup generated by the 3 cycles. So that's clear. I just listed them explicitly. What about now the case for n bigger than 3? So remember what we want to prove. We've already proven that any 3 cycle is an even permutation. Now we want to say that any even permutation is a product of 3 cycles. Okay? Once we do that, we would have completed our proof. So, the good news is there's not a lot of options for even permutations. All right? So, the only possibility is to have a pair, like any even permutation has a number of pairs of transpositions, right? It has a pair that looks like AB times CD. So a pair of disjoint transpositions. The only other possibility is for both transpositions to contain a single common element. So it's going to be AB and BC. And you discover here that these two are the only possibilities to have a pair of transpositions. And since any even permutation consists of pairs of transpositions, this is basically the only possibilities for the building blocks of the even permutations, the atoms of the even permutations. So if we can prove that both of these are equal to some product of 3 cycles, then we would have completed our proof, because these two possibilities make up all the even permutations that there are. So this here, to remind you, this is a disjoint pair containing no elements in common, and there here we have one element in common. So for the first possibility, the disjoint pair, we will write it as ABCD, and that equals to CBD and ACB. Okay? So the way I went about this is I want to see where A is being sent to, where B is being sent to, and where C is being sent to, right? So I know that A is being sent to B. So I wanted A to be sent to B at the end of the day. So A is sent to C and C is sent to B. So that means A is sent to B. That is correct. And for B, well, we have that B is sent to A, and that's it. So B is sent to A, and that is also correct. For C, we have that C is sent to B, and B is sent to D. Therefore, C is sent to D. That is also correct. So this equality is valid, and we have just written this pair of transpositions as a product of 3 cycles. So this is included in the subgroup generated by the 3 cycles. And for the other possibility, we have AB, BC. This could be written as the product BAC and CBA. You can make the same verifications yourself as an exercise, and we can clearly see this is a product of 3 cycles. Therefore, it is in the subgroup generated by all the 3 cycles that there are. So we've just succeeded in proving that all the possibilities for the pairs of transpositions can be written as products of 3 cycles. Therefore, any even permutation can be written essentially as a product of 3 cycles. Therefore, the set containing all of the even permutations AN is contained inside the subgroup generated by the 3 cycles, and we have succeeded in proving the other inclusion. So now we have both inclusions, this and that, yielding us at the end that an is exactly equal to the subgroup generated by the 3 cycles, which is an amazing result, because any result about an, any property about an, it is sufficient to prove it on 3 cycles. And this is what we're going to be doing next lesson. We will see the usefulness of such a result. This completes the proof of the proposition. Okay, so now we've given so much attention on an, the alternating group. But now Sn is feeling lonely now. It's asking if it's also generated by some elements, some permutations. And the answer is yes. And this theorem says that Sn is generated by 2 cycles which are consecutive. So it is generated by the transposition 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, all the way to n minus 1 n, where n is the same n in the Sn. So to prove this theorem, it suffices to see that any transposition AB is an element of this subgroup. So I plus 1, where I ranges from 1 all the way to n minus 1. Because we know that since any permutation in Sn is a product of transpositions, essentially these are the building blocks of all the permutations. So if the building blocks themselves are in our desired subgroup, then it is safe to say that the products of these building blocks are also in the subgroup generated by these elements. So this is the very nice thing about algebra. We don't need to study all of the elements and to see if they're an element in this thing here. We only need to see the building blocks, and because our thing here is a subgroup, so it behaves really well with respect to product and inverses, then it suffices just to work with the building blocks and that's it. It simplifies greatly our proofs. So let us prove now that a transposition AB is a member of I plus 1, where I ranges from 1 to n minus 1. So basically exactly what I wrote here, the consecutive transpositions. So WLOG, saying that without loss of generality, we suppose that A is less than B. Because if B was less than A, then that's just the same transposition, just reverting the order. So AB is equal to BA. We know that the order does not matter in a transposition. Okay, we suppose A is less than B then. Let L be equal to the difference, B minus A. We will perform induction. We will prove by induction. Induction on what? Induction on L. Okay? So if we perform induction on L, we have a base case where L is equal to 1, and then we have the inductive hypothesis to work on. So now let us prove the base case where L is equal to 1. If L is equal to 1, then B minus A is equal to 1, so B is equal to A plus 1. So we have that the transposition AB is just the transposition A plus 1. In other words, this is a consecutive transposition. But if it's a consecutive transposition, then obviously it's inside the subgroup generated by, you guessed it, consecutive transpositions. So it's an element of I plus 1 for all I between 1 and n minus 1. Okay, that is done. Excellent. Now that we have proven the base case for L is equal to 1, we will now use an inductive hypothesis to prove the rest of the induction. So, the induction is set on L. So we have to assume that the result is true for a certain L, and then we have to increase this L by 1 and prove it is true for that one as well. So suppose it is true for L less than n minus 2. Okay? n minus 2 is the number just before n minus 1, the penultimate number. Okay? Let the transposition A be such that the difference between A and B is equal to L. Okay? So the difference of A and B is strictly less than n minus 2. And now consider A, B plus 1. This time, B plus 1 minus A is not less than n minus 2. It's actually equal to or less than n minus 1. So it is not, it's beyond what we have supposed. Okay? What we've supposed is just true for AB, not for AB plus 1. So this is what we're trying to prove. We're trying to prove that AB plus 1 is an element of the subgroup generated by the consecutive transpositions, knowing that AB is an element of that subgroup. So we have that AB plus 1 can be written very smartly as the product of BB plus 1, AB, and BB plus 1. So by making it appear, making the AB appear, we can use the fact that AB is an element of the subgroup generated by I plus 1. Because this is an element, and this, of course, is a consecutive transposition, so it's an element, and that also is an element of this subgroup. So because it's a subgroup, because these three are elements, then the product of all these three has to be an element as well. So this all is an element of the subgroup generated by I plus 1 for all I between 1 and n minus 1. And therefore this element here, this transposition here is an element of this subgroup, and we have completed our proof by induction. So that means that Sn is generated by these consecutive transpositions. If you thought that the previous result was interesting, wait till you see this one. We have, this theorem says that we have that Sn is generated, get this, generated by only two elements, only two cycles, 1, 2, and the cycle containing 1, 2, 3 all the way to n. That's it. Any permutation in Sn can be generated by products of these elements or their inverses. What's more impressive than the theorem itself is that the proof is only done in 3 lines. First line is that we have, by the previous theorem, Sn is generated by consecutive transpositions. The second line, for all I, we have. The third line will complete the proof. How crazy is that? We have I plus 1. So because Sn is generated by consecutive transpositions, all what we need to prove is that the result is true for a single consecutive transposition, no matter what I is. Once we have done that, we have proven the result for all Sn. How crazy is that? So I plus 1 is equal to the product of 3 cycles, which I will be writing here. Admittedly, they would look complicated at first, but after I explain, it will be much easier to deal with. So the first cycle is the cycle containing 1, 2, all the way to n. This cycle, I will take it to the power I minus 1. The second cycle is the transposition 1, 2. And the third cycle is the inverse of this cycle here. So n minus 1 all the way to 2 and 1. And that I take to the power, again, I minus 1. Now, I will explain to you why this equality is true. The reason it's true is because if I take only 1, 2, all the way to n, okay? If I label this as sigma, the permutation 1, 2, all the way to n, then sigma of 1 is equal to 2. Sigma of 2 is equal to 3. So 1 goes to 2, 2 goes to 3, and so on, right? What if I square this? Then if I square this, and I write this again, multiply this by itself, I'm going to get that 1 goes to 3, and 3 goes to 5, and 5 goes to 7, and so on. So instead of adding 1, I add 2. So sigma squared of 1 will be equal to 3. Sigma squared of 2 will be equal to 4, and so on. So I'm going to add 2 instead of adding 1. If I take the third power, then sigma 3 of 1 is going to be 1 plus 3, which is 4. Sigma 3 of 2 will be 2 plus 3, which is 5. So the power here will indicate how much I'm going to add to 1. Okay? So here we took I minus 1. So the power is I minus 1. And this here is I minus 1. And this here is I minus 1. And that here is I minus 1. Right? So sigma of 1 is equal to 1 plus I minus 1. And that is equal to I. Okay? Sigma of 2, so 2, sigma to the I minus 1 of 2 is 2 plus I minus 1, which is equal to I plus 1. Okay? So keep that in mind as we move through this equality here. So this is all well and good. What about this other one here? We will use the same kind of logic to deduce where does this send each of the elements to. So if sigma is equal to n minus 1 all the way to 2 and 1, then sigma of n is equal to n minus 1, sigma of n minus 1 is equal to n minus 2, sigma of 2 is equal to 1, and so on. So it subtracts 1. And if I do a square, then it subtracts 2. If I do a cube, it subtracts 3. So if I do an I minus 1, it's going to subtract I minus 1. So this becomes n minus I plus 1. So here we're interested in seeing where does all of this send I to? And where does all of this send I plus 1 to? We wish to see that all of this is going to send I to I plus 1, and it's going to send I plus 1 to I. And it's going to fix everything else. So we want to see where it sends I. So let us say there is an I over here, and we want to see where it goes. So here, I is going to be sent to I minus 1. because we've said that we subtract I minus 1 here. And this is equal to I minus I is 0, minus 1 is 1. So it's going to be sent to 1. And here, 1 is going to be sent to 2. And there, 2 is going to be sent to 2 plus I minus 1. Because remember here, we add I minus 1, we add the power. So 2 plus I minus 1, which is I plus 1. Hey, we've just sent I to I plus 1, just like in the transposition here. So they both send I to the right place. And now, where does I plus 1 get sent to? We wish to see that I plus 1 is getting sent to I. So I plus 1. So here we will have to subtract I minus 1. And this equals to I minus I is 0. 1 plus 1 is 2. And 2 is being sent to 1. And 1 here is being sent to 1 plus I minus 1, which is equal to I. So indeed, I plus 1 is being sent to I, just like what we wanted. I plus 1 is being sent to I. So this is awesome. We have that both sides of the equality send I to I plus 1 and I plus 1 to I. They send them to the same places. What if the element was neither I nor I plus 1? Well, since the left-hand side, we don't find any such elements, then they are fixed. They are not sent anywhere. They're sent to themselves. So we want to see the same going in the right-hand side. Well, if you look at the right-hand side, intuitively speaking, we see 3 cycles, this, and that. We see that this cycle here is the opposite of this cycle. So this is the only thing that flips. And if the element here is not being sent to an element that is either 1 or 2, then this guy here is going to take care of the inverse, and we're going to go back to the original element, therefore fixing our element. So as long as we don't end up in this hole here, we're going to fix our element. And I'll tell you what that means mathematically. So if our element is not I nor I plus 1, so if j is not equal to I, and j is not equal to I plus 1, and j is an element between 1 and n minus 1, then we know for a fact that if we put it here, so j minus I minus 1, j minus I minus 1, it's not going to be equal to I minus I minus 1, which is equal to 1, right? So it's not going to be equal to 1, and in the same vein, we can see that it's not going to be equal to 2. So it's not going to go here nor here. So it's going to just completely skip over this cycle, and it's going to go immediately here. But here, what we're doing is we're adding I minus 1. So here we're subtracting, and here we're adding. The same thing. So at the end, it's like we did nothing. You know, we went from j to j. So we fixed j. And all of that is because we did not end up in the cycle that changed 1 to 2 or 2 to 1. And that's why the right-hand side fixes any j that is not I nor I plus 1, the same way that the left-hand side does. So we have just proven this magnificent equality that the consecutive transposition I plus 1 is the product of this thing here. But this thing is nothing but something that is generated by these two elements. You can see the 1, 2 is right over here, and this is a power of this element, and this is a power of the inverse of this element. The inverse being n and minus 1 all the way to 2 and 1. And therefore, because Sn is generated by consecutive pairs, consecutive transpositions, and each consecutive transposition is in this form, then we can say that Sn is equal to the subgroup generated by 1, 2, and 1, 2, 3 all the way to n, completing our proof of this magnificent theorem. We now move away from symmetric groups, alternating groups, and go in the territory of matrices. In matrices, we have said that GL2Z and SL2Z are groups. To refresh your memory, I suggest you go to lesson 6, but here I'll give you a quick recap. SL2Z means the special linear group of order 2 with coefficients in Z. It is the group of all matrices of all 2 by 2 matrices with coefficients, with integer coefficients, such that the determinant of these matrices is equal to 1. So we know it already that this is a subgroup of the general linear group because it is the kernel of the homomorphism, the determinant of matrices. For a theorem, we have that this SL2Z is generated entirely by 2 matrices. S given by this matrix and T given by that matrix. And I will be proving this theorem. To prove this theorem, let G be equal to the supposed subgroup generated by S and T. We prove that SL2Z is equal to G. That is what we want to prove. Notice if A, B, C, D is some matrix in SL2Z, then what does the action of multiplying a matrix S or matrix T by this matrix give us? We want to explore what happens. So if we do S times A, B, C, D, what does that give us? That gives us minus C, minus D, A, and B. So essentially, it swaps the positions of row 1 and row 2, and it changes the sign of row 2 as it swaps. And if we multiply T to the n, so T times itself n times, by A, B, C, D, the product is going to be A plus NC, B plus ND, C and D. So this is what the product of these matrix multiplications that we have from S and T. We're going to make good use of these products now. Let gamma be defined to be the matrix that we've already said, A, B, C, D. So it's some matrix in SL2Z, some arbitrary matrix. Okay? We want to prove that gamma can be written as a product of S's and T's. Okay, here we're going to do something quite peculiar. We're going to make use of what is called the division algorithm. If the absolute value of A is greater than or equal to the absolute value of C, then we will divide A by C. Remember, all of the coefficients here are integer coefficients because we are in SL2Z. So when we divide A by C, we will use the division algorithm to say A is equal to QC plus R, quotient and remainder, where the remainder is between 0 and strictly less than the absolute value of C. And when we get the R, we will say that R is equal to A minus QC here, and then we will multiply the gamma by t to the minus q. So n is equal to minus q in our case, t to the minus q of a, b, c, d. So using this algorithm here, we get a and n. Remember, n here in this case is minus q, so it's a minus qc, and here it's going to be some number that I don't care about. I'm just gonna write star, and here it's going to be c and d, just like it's written over here. Okay, what I care about the most is these two numbers here. A minus qc is exactly equal to r, so that's what I'm going to write, r star c d. Okay, now I want to multiply this product by s. So s times r star c d, and what that's going to give me is exactly what is shown here. I'm going to flip C and D, I'm going to give them negative signs, and the R is down bottom, and the star is down the bottom here. And this I will call my new gamma 1. So now that we have the new matrix gamma 1, if R is not equal to 0, here, we're going to repeat the process. Basically, we know that the absolute value of R is less than the absolute value of minus C. So this condition is already fulfilled. So we repeat the process since the absolute value of minus C is greater than the absolute value of R. And we will get that minus C is equal to Q1 times R plus R1 for some R1 that is between 0 and the absolute value of R. Well, we know that the absolute value of R is just R because R is positive here. Okay, great. So we repeat the process and we perform another matrix multiplication. So we get t to the minus q1 times gamma 1 is equal to, this time, we perform the same sort of algorithm here to get R1 up top and R down below. And on the right hand side, I do not really care what I get. All what I care is about is the left column. And whatever I get here, I will multiply by s. So s times t to the minus q1 gamma 1 gives me minus r1 star star. So notice that each time I perform this algorithm, the number I obtain here gets smaller and smaller. It's a positive number that gets smaller and smaller. So since it's an integer, I'm having a sequence of positive decreasing integers that approach 0. So I'm bound to reach 0 at the end. So, and so on, till I reach, or till we get a lower left entry of 0. Once that happens, I stop my algorithm. And I obtain a matrix which we call gamma star. So gamma star is the matrix obtained when this lower left corner is equal to 0. Let gamma star be this matrix. Okay, so gamma star is of the form A star, B star, 0, D star, right? Where A star, B star, D star, where A star, B star, D star are all integers. Okay, since gamma star is an element of SL2Z, we must have that the determinant of gamma star is equal to 1. The determinant being equal to A star times D star minus B star times 0. So it's just equal to A star times D star. So this means that A star D star is equal to 1. But since A star and D star are integers, the only integer solutions to this equation are A star D star being either 1 or minus 1. So in the end, we don't have many options for gamma star. Gamma star is either 1, m, 1, 0 for some m, which, by the way, is because this is because t is 1, 1, 0, 1, t squared is equal to 1, 2, 0, 1, t cubed is 1, 3, 0, 1, t4 is 1, 4, 0, 1. You can check that out by multiplying matrices together. So t to the m is 1m 0m 0, 1. So this matrix here, with diagonals 1, 0 here and m there, is equal to t to the m, or remember, it could be minus 1 on the diagonals. So minus 1, 0, and m. But with a little manipulation, this is minus 1, 1, 0 minus m, and that is equal to minus t to the minus m for some m and z. Okay, so to recap, we've started with an arbitrary gamma, an arbitrary matrix in SL2Z, and by performing a series of multiplications, we've arrived at some product of S's and T's times gamma star, which is equal to either t to the m or minus t to the minus m. But since, if you look at S here, S squared is equal to minus 1, 0, 0, which is equal to minus I. Minus I, this gives us the negative sign here that we want. That we want where? That we want here. So this could be equal to minus I times t to the minus m. And I times any matrix, since it's the identity matrix, we can just put the I there, no problem. And that is equal to S squared t to the minus m. So there exists a g in G such that G times gamma is equal to plus or minus t to the n for some n and z. And this means that gamma is equal to plus or minus G inverse t to the n, which equals to minus I to the power k for some k. If k is equal to 1, then this is just equal to minus I, and we would get this. If k is equal to 2, then we would get this is equal to I, and we would get this. So either way, we would get both possibilities. Times G inverse times t to the n. And this is equal to S2k G inverse t to the n. And if we look here, this is a member, this is an element in G, this is an element in G, and this is an element in G. Therefore, their product, of course, is an element in G. We've just succeeded in saying that any arbitrary matrix in SL2Z is an element in G, where G is equal to the subgroup generated by S and T. So we've just successfully said that SL2Z is equal to the subgroup generated by S and T, completing the proof of this theorem. The last part of this lesson is a fun exercise in visualizing groups and subgroups. It is called the lattice of subgroups of a group. The first example being if we have the cyclic group C12 of 12 elements, all the subgroups can be found in the lattice here. Starting with the biggest one, the biggest subgroup, of course, being C12 itself, we have the subgroup of 6 elements, G squared, generated by G squared, so it's 0, G squared, G to the 4, G to the 6, G to the 8, G to the 10. And here we have the cyclic subgroup of 4 elements, the cyclic subgroup of 3 elements, the cyclic subgroup of 2 elements, and the lines here just say that this is a subgroup of that. So here, for example, this is a subgroup of that, and here this is a subgroup of that, and here the G6 is a subgroup of both G to the 3 and G to the 2. So it sort of reminds you about the factorization of integers that you've taken in elementary school. Remember when you had 12 and then you divided it by 6, and then you had like a 2 here and then a 3 and so on. And it's the same sort of idea where you decompose your group into subgroups and you see which subgroups are subgroups of which subgroups, basically. So this, having an order of 2, divides this, which has an order of 4. So the order of this is 2, the order of this is 4, 2 divides 4, so we have that. Here the order is 6, so 2 divides 6. However, 4 does not divide 6, so clearly there is no line in between those. Okay? Here this has an order of 3, and 3 divides 6. And here this has an order of 1, 1 divides 3, 2, 4, 1 divides 6, and so on. So this is the first example of a lattice. The second example is a bit more complicated. It's the dihedral group of a square. We have D8 generated by rotations and symmetries. Now we have the subgroups is S and R square. We have the generation by R. We have the generation by SR and R square. And each of these subgroups have orders that divide the order of the group. And these subgroups here are subgroups of SR square. This is a subgroup of all 3 here. And these 2 are subgroups of this one here. So I'm not going to go too deep into it. I'm just going to let you have a good look and play with the subgroups yourself to see what each of these generate. What is the generation of these? So to play around with that, I invite you to try and find what the products of these elements are with themselves, with each other, the inverses of these elements, what do they give, and try to generate the entire subgroups and apply this for all of the subgroups in this lattice. So this terminates the lesson for today. Please like and subscribe, share with anyone who would be interested in such a nice topic, and I will be providing more content on this course, plenty more lessons to come. Have a nice day and bye.